Good morning, eighth graders. So we are now getting into more of the macro idea or the big picture of the Earth and where all of our rocks and minerals, excuse me, come from in order to be where they are today and form what they have formed and all this other kind of fun jazz. So we are talking Earth structures, or essentially looking at the layers of the Earth and what's really happening below our feet. There's a lot going on, and there's a lot more below where we can see right now than I think we really even know. So we are working with two different standards this unit. So we're working with Earth Science Standard 2-2 and 2-3. 2-2 states that you will be able to construct an explanation based on evidence for how plate movement has changed Earth's surface. So why does our surface look the way that it does? And then 2-3 states that we will be able to interpret the different forces acting on tectonic plates and the location of where they occur in relation to various boundary types. We will get into that in a couple of weeks. But kind of leading into that, we also need to be able to analyze and interpret data on the distribution of fossils, rocks, continental shapes, and sea floor structures to provide evidence for how we know that the plates have moved over millions and billions of years now. So by the end of today, though, we're not really going to hit a lot of these standards, but because we have to understand how the Earth truly looks moving inward before we can start explaining some of these things. So this is the very basic ground level information we have to know. So some of this is going to be review, but a lot of this may be brand new information to set the basis for hitting these targets in the next couple of days. So by the end of this unit, you should be able to explain the tectonic plate theory and can provide evidence for how we know that this is what's happening. Construct an explanation using evidence to demonstrate how convection currents drive plate tectonics. We're going to talk about convection currents today. And then analyze and interpret data to provide evidence for past plate movements such as fossils, rocks, Pangea, and continental drift. So it's a lot, but we are going to take our time to get to know all of this information, starting with just the very basics. So in order to kind of be successful throughout this portion of the lesson, you need to make sure that you have your Earth structure notes in front of you, and all of your front pages should look like this, okay? We will explain so much more as we go. So let's get into this. So let's look at the layers of the Earth. I love to talk about how the idea of the Earth is that it's like a giant jawbreaker. There is so much happening, so many layers, that it does essentially look like this if you were to cut into a piece of it. So we're going to talk about each of these different structures and what they truly mean and more in-depth information about them. But there are two major ones that we're going to need to cover, and they're probably the two you have never heard of. So we are going to cover the lithosphere and the asthenosphere. So here is a not to scale. Why I have to say things like this is ridiculous, but this is not to scale of a cross-section of our Earth. So when we have talked about the Earth before, and by we I mean like your elementary teachers, because these are probably some of the like fun, like, oh, let's learn about the Earth, little science lessons that they do bring in. But when we talk about the Earth, you've probably only really heard of 4, maybe 3 major layers. Coffee first. So you've probably talked about the crust, or the part that we stand on. You've probably talked about the mantle, which is kind of the inner ooey gooey portions, and then the core, whether you've talked about the inner versus outer, but you've probably talked about the core. So these are the 3 you have probably covered. Okay, now what we need to understand is there's actually 8, sometimes more, depending on whom you speak with. But we are going to focus in on 8 major ones. So we have the crust, but we have to understand that there's actually 2 types of crusts. Okay, so we have, let me see if I can switch my color. I'm going to go with the dark blue. So we have this oceanic crust, or crust that is underneath our oceans. We cannot physically stand on it, but it is a solid mass at the bottom of the ocean. And then we have continental crust. Okay, this is where we are currently standing. Now, obviously, ours don't have mountains, but we will talk about that as well. So there's 2 types of crusts. Then as you move your way down, before you even get into the mantle, we have this cool little layer that is called the lithosphere. Now the lithosphere covers all of the continental, all of the oceanic, and the very top portion of the mantle. We'll talk about that configuration and what that truly is as far as its state of matter, but we have to understand that the lithosphere is the main portion we're going to be focusing on, because the lithosphere is also known as our tectonic plates, or how each landmass is moving on top of our mantle. Okay, so we have our 2 types of crust, our lithosphere, which covers the crust in the uppermost part of our mantle. And then right below that, within our uppermost mantle, we have the asthenosphere. Now, I need to choose a color that'll show up on here. The asthenosphere is this really cool layer that is I almost want to call it like slime, where it's technically solidish, but it's able to move and manipulate. The asthenosphere is really important when it comes to understanding our plate tectonics, because this is where the movement happens. Okay, so crust, lithosphere, asthenosphere. Then we get into our middle mantle, our lower mantle, there's the uppermost mantle, all that fun jazz, and then the outer and inner cores. We are going to talk about the difference between the outer core and the inner core. There's just a lot to cover. So that's kind of just the basics right now. Understanding that there are those 8, 9-ish layers, but it makes up so much. And we're going to talk about the depths and how we are able to see through the earth, even though we can't dig through the earth, and all this kind of fun stuff. So hang in there. This is probably going to be a little bit on the longer side, but honestly, this is information you need to know in order to understand each and every topic and unit that comes from here on out. So that is the end of whole group. Make sure that if this is it for you, that you're following your champ's expectations. But if you are following along for PowerPoint, keep it in mind as well. But also, don't be afraid to ask questions. Okay, so reasons for the layers. So this is really fun. Layers are determined by 3 criteria. Remember, criteria are things that have to be met. So composition, what are they made out of, really helps define each of our layers. Their depths, so where they land, as far as closest to the surface or furthest from the surface. And then their states of matter. We have talked about how states of matter would be like solid, liquid, and gas. And that is also to be said for our Earth, is that we are not all 100% solid. And we will talk about all of our liquidy parts kind of moving through. So that is how we are able to define each of these layers. So we're going to go more in depth, but I just wanted you to know that this is how we know the crust is where it is and the outer core is where it is. Okay? So crust, more than just on your sandwich. Okay, so our crust is the least dense layer of our Earth. That is why it is on top. Our crust is where we can stand. It is where humans and animals and plant life and everything is able to coexist. Typically, when we're talking crust, we're also talking about interaction with the hydrosphere or the atmosphere, or both. So this is the least dense portion of the geosphere, or our Earth. That is because it's made up of primarily silicon and oxygen. We talked about this when we talked about rocks. 90% of our rocks are made out of silicon and oxygen. That's why they're called the silicates. We get more of those dense rocks the closer we get toward the mantle. So those will be closer in your oceanic crust or deeper within our continental crust. So let's talk about this different. Continental crust, which is our land crust, it tends to be 4 times thicker than the oceanic crust, but it is much less dense. The example I love to give, because to me it makes the most sense, remember, you don't always have to go with what I say, but roll with me. So our continental crust is like a dry sponge, okay? A dry sponge can honestly be really, really thick, okay? But there's a lot of air pockets within this sponge. But if you were to set it on top of water, it would float for a while till it gets too wet. But it's much less dense. There's more air in between everything. And the same can be said for our continental crust. Versus our oceanic crust, which is made up of crustal rock, which is much denser than continental crust. It's like taking that sponge and just squishing it. You aren't adding anything new. You just are taking away that extra air pocket to where it just becomes more dense and heavy, it is more difficult to try to get through rather than trying to get through the air pockets on our continental crust. So that's the difference. Other examples, which we'll come to at the end of the unit, is like the difference between a graham cracker and a Rice Krispie treat. Okay, pretty much the same, but one is much, much thicker, one is much less, or is much more dense. So they interact differently. Okay. The average temperature of our crust is about 14 degrees Celsius, and that is because we're taking into consideration the crust that is outside, right underneath our snow right now, all the way to what is closest to the mantle. And what we have to remember as we go deeper into the Earth, the hotter it gets. So as depth increases, temperature and pressure increase as well. This is where we're able to get those really awesome metamorphic rocks and eventually turn into igneous rocks because they're completely melted. Okay. The thickness of this layer is anywhere on average from 15 to 20 kilometers. I don't necessarily like that. Typically we can say it's about 0 because there are some spaces in the oceanic crust mainly where there's not very much, so less than a meter or so, all the way as deep as like 100 kilometers. So just 15 to 20 I think is a good safe space. And as we look at this next layer, this next slide, you'll be able to kind of see why. So with our crust, because we have all of that intense pressure that is happening underneath all the weight of the ocean, this is where we get oceanic crust, which is very, very thin, but very, very dense. If you imagine trying to dig through wet sand versus dry sand at the beach, okay? So it's like digging through that wet sand, really heavy, hard to move. Versus you get continental crust, which if you go to the highest peak of our mountains, all the way down until you were to meet where the mantle comes into play, it's very, very deep, but it's not necessarily very, very dense, meaning that there's still more of those air pockets in between. Yes, compaction is happening. Technically, the Earth is like a giant sedimentary rock, but there's still spaces. Caves are a great example of this. Okay, they happen. So those are our two types of crust. The lithosphere. The lithosphere is this really weird but super cool layer that combines the crust, so both oceanic and continental, and the uppermost part of the mantle. The mantle is really, really thick. I want to say the research I was seeing was like the mantle makes up about 88% of our entire Earth's mass. So it's big. Now, the lithosphere, you can kind of see it here, but let's see if I can find a color that will work. So it is all of this crust, and then to this uppermost portion of the mantle. Okay, this all sits together. It doesn't really, yes, you have this separation, but it's more like a blurred line where it all sits together, and this is what is moving all of our landmass. This is our landmass that is able to move. Now, because we're getting deeper in the Earth, we are getting to more of those heavier elements. So yes, the crust is mainly silicon and oxygen, but then you get that uppermost portion of the mantle, and that is where you start to get that iron and magnesium, so very heavy metals within the mantle. Now, the state of matter, it's not really a state of matter, but the lithosphere is this really cool, solid, but rocky and brittly sort of makeup. If you were to imagine the top crust of a brownie, that's kind of what's happening, where it is solid, but it can break apart really easily and kind of sort of meld itself into whatever else is around it. So it's able to move, it's able to melt, it's able to crash in and make new sorts of things. But for the most part, we're going to call it solid. Okay. The temperatures, well, because we're at the crust, we're at about 14 degrees Celsius, but all the way towards the bottom portion of the lithosphere, we're reaching anywhere to about 1,280 degrees Celsius. Remember, the deeper you go, the increased heat and pressure. So it's going to get hot as we move towards the center of the Earth. The thickness of the lithosphere, because it is the crust and the mantle, uppermost part of the mantle kind of combined together, it ranges from about 30 kilometers to 50 kilometers deep on average. Now, it's going to be deeper when you're thinking like underneath Mount Everest, but that's only one portion of the entire world. Okay? The mantle, and I'm not talking about what's over your fireplace. So the mantle is, I'm sorry, I'm apparently getting the cold that both the boys had. So this is the thickest middle portion of our Earth. This is where magma is found. So when volcanoes erupt, this is where we get the molten rock that comes up through it. It contains a lot more iron and magnesium. Granted, you still have silicon and oxygen mixed in there. You're going to see a little bit of silicon and oxygen mixed in until we get to the inner core. But these are very dense elements, meaning that they're very heavy. They're heavier than what the crust is at, and that's why we can have the crust floating on top of it. If you were to think like oil and water, you have the oil, which is the crust, and the water, which is the mantle underneath it. Now, there are technically 4-ish layers of the mantle. But remember, the uppermost part of the mantle is what is connected to our lithosphere. So this is that rocky, brittly makeup, similar to the crust, higher amounts of magnesium and with silicon and oxygen still mixed in. It can reach an average about 227 degrees to 3,930 degrees Celsius, but that's mainly the range from the uppermost mantle down to the lowest portion of the mantle. Because the mantle is so complex, scientists aren't really able to put better numbers to all that. Right below the uppermost portion of the mantle, which is a part of the lithosphere, we have this special little layer called the asthenosphere. Now, I don't know why all scientists apparently don't have a speech impediment, because the names that we come up with, they're hard to pronounce. So lithosphere sits on top of the asthenosphere. The asthenosphere is this really cool viscous or plasticky sort of layer. Now, when I was taught viscous, it was like understanding the difference between water, which flows very, very easily, as compared to syrup or molasses. Now, not warmed up syrup or molasses, room temperature, where it takes a lot more effort for it to move, but it moves similar to a liquid. So the asthenosphere is like that molasses or slime, whatever like you can actually like picture in your head, where it's able to move, but it's not moving free flow like water or air, but it's also not sitting still like solid rock. Now, the chemical makeup of this, it's mainly ovalene or ovalene, however you want to say it, and pyroxene, which is essentially just fancy rock terms for saying calcium, sodium, iron, and magnesium. That's what's going on. Temperatures are so hot, we're sitting at about 1,700 degrees Celsius, to where the rock begins to kind of melt. This is where, if you were to imagine metamorphic rocks, this is where metamorphic rocks are hanging out. Because the rocks are starting to melt, they're able to actually flow very slowly. And they flow thanks to this like heating and cooling cycling called convection currents. Convection currents are what we need to know. So essentially, if you were to look at a lava lamp, you have the heat source at the bottom, you have this weird goo sitting in colored water typically, and as it heats up, it starts to rise, and as it meets the cooler temperatures towards the top, because you don't have that light source at the top, then it starts to cool and become heavy and fall back down. That is convection. We see this in dozens of places. My room is not a great example. My room is 1,005 degrees all the time. But typically, I always like to ask my learners, in the summer, where do you like to hang out? Would you much rather hang out up on the top floor of your home or apartment building, or would you much rather hang out on the bottom or the basement? Okay, typically they're going to say, well, basement, because heat rises. Okay, when Mr. G and I lived in an apartment, loved the second floor. Like out of a 3 to 4 story building, loved the second floor because you get all the heat coming up from the first floor, and then some cooler air to where it always sat nice. I don't think we ever really turned on the heater in our place, versus our first home was a split level. We could never get it to sit the right temperature. Will had a like standalone heater going on in his room because his room was on the bottom floor, and as a baby they need to stay a certain like temperature, versus now he'd love it. But because it was so cool, because all that hot air rose, versus Mr. G and I were dying upstairs because we both prefer it cooler, and all this or whatever. So that versus now, whole new issues. We won't get into that. But convection is what allows that to happen, is that hot air rises, but as soon as it starts to get away from the heat source and cool down, now it starts to flow downward. And that's what's happening with this rock. And on the next slide, we'll look a little bit more into it because it's a far better descriptor. But I just wanted to kind of explain that, because that is what drives our lithosphere to being able to move. Okay, moving on. Down below the asthenosphere, we have our upper mantle, which is more of a solid layer. Typically, things are solid because of the amount of pressure being placed down on it. So again, we have that range of 227 to 3,930 degrees Celsius, but we for sure are sitting warmer than 1,700, but not quite all the way to that 3,930. So somewhere in between there. Call it a good 250. Okay. These are ultramorphic peridite rocks. Remember mafic when we talked igneous rocks? These are the really dark, heavy element rocks, very, very rich in magnesium and other silicates. So that the upper mantle we assume is about 2,900 kilometers thick. Now that is from probably more so that uppermost mantle to that bottom lower mantle. Okay, and then finally the lower mantle. This is like the jawbreaker that never ends. So the lower mantle is again another very solid layer. There is a lot of bridgemanite, ferropericlast, and calcium something or other. I can't see because when I start recording my thing goes right in the bottom. Basically, iron, magnesium, some aluminum, silicon, oxygen, calcium, apparently, thrown in. That's a lot of very heavy stuff. Now, your amount of aluminum and silicons and oxygens are going to decrease compared to the amount of magnesiums and irons. Okay? This is where we're feeling a lot of that heat, so that 3,930 degrees Celsius. And the lower mantle, again, is not as thick as the upper mantle, but it's still pretty thick at 2,340 kilometers. Okay, so that's our mantle. Now, hold with me as we get to the next slide. So convection currents, because this is the best indicator, I feel. I'm gonna grab my little pen. So the inner core, as we have talked about many, many times already, the deeper you go into the earth, the hotter it gets. This is a struggle bus. Okay, the hotter it gets versus up at the surface, like, yeah, no, we're sitting out here and it's like 20 degrees right now, Fahrenheit, about 0-ish degrees Celsius. And we're like, oh my goodness, that's so cold. It is really cold compared to where we're going as far as the inner core goes. So as the inner core heats up, imagine this kind of like a little sun, okay? It is allowing this rock to start to flow. And what happens is that it gets to a point and it starts heading upward. And now there's something with like centrifugal force and all this. Mr. G can answer that far better than I can. But as it rises, it tends to rise in a similar direction. But once it gets up here toward the crust is significantly cooler. If we're looking at like this layer, now let me fill it in with black. If we're saying this black layer is 3,930 degrees Celsius, and we're saying up here at the crust is a cool, what did we say? Now my numbers are escaping me. We were not at 40 because that's hotter than hot. 14, I think, is where we were at. If we're sitting at 14 degrees Celsius, typically, I'm no mathematician. That's a lot hotter. To where once it reaches up toward the crust or the bottom of the lithosphere, it starts to cool very, very quickly. And then once it starts to cool, it starts to fall. Okay? This is convection. This is the lava lamp where you have the heat source pushing the goop up, it cools down towards the top, and it falls back down, and it continues this cycle. That's convection. This is all happening. The convection currents are mainly within the asthenosphere, but you get all that heat coming up from the inner, outer, and the lower portions of the mantle, heating up that like viscous sort of molasses slimy rock that can then move. okay? And we will talk about like more of this diagram in a couple of days, but as it moves, then the weak portions of our slabs or our plates, they start to move with the flow, okay? So we'll talk more about that, but that's what's going on. It's kind of intense. Now, there we go. Anyway, now this probably won't play in here because why would it ever? So I'm just going to quick bypass it. I'm going to link this YouTube link into the Schoology folder, but this is another great example. It explains it far more thoroughly than I can. The guy does have a really weird accent right away. It is Australian, but it's a shocker every time I hear it right away. So that's what's going on in there. So I'm going to bypass it, so make sure that you stop this video for a minute, go watch this one, and then come back, okay? So now we're at the cores. We're at the very centers of our Earth. Now the cores, there are two separate cores. We have the outer core and the inner core. The outer core is this liquid molten rock. Now, why is it liquid? Well, there's so much heat and pressure that it just cannot stay solid. It's a really weird phenomenon that happens, okay? But this is a lot more of an iron and nickel sort of mixture with a very, very small amount of silicon and oxygen. We are looking at temperatures between 2,700 degrees and 4,200 degrees Celsius. Remember, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. That's where we're at. Within the outer core is where we have another really cool phenomenon happening. We get the magnetosphere. We're going to talk about the magnetosphere a little bit more. It's not just a cool superhero name, or wasn't Magneto like a bad guy? I don't remember. Anyway, but because you have this liquid metal essentially getting spun around very, very quickly, because our Earth rotates very quickly within our solar system, we then have metal that's like hitting each other and all this or whatever, creating this magnetosphere, which is essentially why we know where north versus south is without a GPS. Okay, so the outer core, that's why it's important, and that's why like we're like, oh, this is why it had to happen. I don't know. Okay, and then our inner core. So finally, once we get all the way into the center of the Earth, we get this solid piece of metal. There is so much pressure that it cannot be in any other state other than solid. And that's because it is 80% iron and about 20% nickel. There's a little bit of other things thrown in there, but this is like the main thing. But it's sitting at a cool 5,430 degrees Celsius. So it's very, very hot. That's why like in the example with convection currents, you have to imagine it like a mini sun within our planet. The radius, so from the very, very middle out to the edge, is about 1,950 kilometers. It's not very thick as compared to the rest of the Earth. So that's what's going on. Now, I have like 4 more slides that I want to talk about, and it's talking about all these little intricacies that keep our planet alive and allow for life to actually work. And I know that this is already pushing a really long PowerPoint, but hang with me, I promise. So there's liquid beneath us. And because of this liquid, this is why scientists are actually able to see what our planet looks like, how it is like this jawbreaker. Because scientists use seismic waves or shock waves made by earthquakes and explosions and track them as they travel through the Earth. These waves experience different levels of, now, okay, mind you, let's read this for a second. I did not write this, but I can explain it. Mr. G wrote this. He really understands waves far more than I do because it's physics. I don't like math. Okay, so the waves experience different levels of refraction. Let's talk refraction quick. Refraction is when a light beam or a wave of some sort, sound, light, other waves, I don't know, comes in contact with something and then veers off. It doesn't go through, it doesn't whatever, it hits and then it bounces off in a different direction. Think of, okay, I'm going to pong, little like slider thingies, and then the ball beep, and all this. I'm sure you guys have a new game that's the same thing, but it hits off into a different direction. Okay, so that's refraction, or even reflection, which is like looking in a mirror where it just kind of goes opposite, but it goes through as they hit layers where the density changes. Okay, so we know that this is what our Earth looks like based off of following seismic waves through it and how they kind of scatter depending on how deep they get. They measure these changes to figure out the density of the rocks and its composition. Math. This is like the only part where it's like, oh, math making sense with like the Earth. So because we follow those waves, thanks to tectonic plate movement, because that's how we get earthquakes, getting there, that or whatever, plus then just explosions and things like that that happen on Earth's surface, we have been able to essentially scope out what our Earth should look like if we were able to actually cut into it. I find that really interesting. I wouldn't put it like this, but Mr. G knows what he's talking about. I'm just following along. So, because we are watching essentially waves that happen around here, the way that they bounce, the way that they kind of veer off, the way that they bounce, veer, bounce, all this kind of stuff or whatever, and then come back. That's how we're able to tell that there's all these different layers, because as a seismic wave, let me clear all this off quick. As a seismic wave comes in contact with a new boundary, it does something different. But no matter where that wave is coming from, once it hits that same boundary, it does the same sort of bounce. Okay? Again, math. But yeah, that's how we're able to tell what's going on underneath. Now, we talked super quick about why is the outer core liquid? Why do we care that it's liquid? And that's because why it's liquid, not 100% sure. We're assuming heat, pressure, it couldn't solidify. But why do we care is because it's responsible for our magnetic field, or our magnetosphere, essentially telling us with a basic compass which way north is versus which way south is. So the movement of the liquid metal gives off this electric current. That's all magnets are, is essentially how electric currents can run through them. It's not always accurate, okay? We speed up, we slow down within our rotation, we get Mercury in retrograde, all this other kind of fun jazz, to where the direction and the strength can vary depending on the geologic activity happening. Okay, it gets weird around earthquake faults. It gets weird around volcanoes. It gets weird the further you are up in the mountains versus how close you are to sea level. It just happens. It's nature. It's not perfect. And then to top it off, we actually have rock evidence to show that there have been several times within history that the direction is actually reversed, where the North Pole is no longer the North Pole. No, the Earth does not flip. Okay, it's just the way that the electric currents are moving to where north moves towards the south and south moves towards the north. Okay, the magnetic pull, not the physical Earth. Okay, so we can see that within our rock layers. I find that part fascinating. So the magnetosphere or the magnetic field are parts of the magnetic field that surround Earth. Essentially, our Earth is a giant magnet. And just like convection currents, they kind of move in the same direction and come back toward the same direction. This allows for some protection, because if you have electric currents going through, it is currently 6:07 in the morning. I'm hoping he doesn't wake up. Anyway, it provides some protection from rocks and asteroids and meteors coming from space to kind of get broken up. It also allows for those extra charged particles that are given off by our sun to kind of get chilled out before it reaches us and cause UV damage. You still get some UV damage. Again, it's nature, it's not perfect. Okay, but it's just another added protection that keeps us alive. So that was a very in-depth look at depth. Pun not intended, but I like it. A very in-depth conversation about our Earth and how it's more than just 3 or 4 major layers, but rather it's 8 or 9, depending on how you want to look at it. But again, the major points that you need to take away from it are the lithosphere versus the asthenosphere, and the fact that within the asthenosphere is where our convection currents are happening, because that is what drives the rest of this unit. Okay, the rest of it's good to know. And I know that we're going on 40 some minutes, and I'm really, really sorry. I try really hard to keep these lower, but we had to cover all of that. So thank you, thank you, thank you. If you 100% made it through this video, I would be honored to give you a Genie cheer or something like that, because by you coming up and asking for that tells me that you actually listened to all 40 some minutes of this. So thank you, thank you, thank you. And if you have any questions, let us know. There is a check-in after this, so make sure your notes are complete, your check-in is done, and then we will move on to the next step. Awesome. Thanks, 8th graders. I really appreciate it.